So we've talked a little bit about potential energy for gravity, and so let me make a few statements about potential energies and where they come from. So a potential energy is the energy a system has due to its position, shape, or configuration. So, if I raise an object in a gravitational field, I'm increasing its potential energy. What I'm really doing is I'm causing gravity to do negative work, and anytime I cause it to do negative work, I can always get it back in positive work by just dropping the object. Same thing with a spring. If I work against a spring, if I just hold this guy stiff, when I move this guy out, I'm doing positive work against the spring, but the spring's pulling that way, but moving this way, but pulling that way. And so it's doing negative work, and anytime I want, I can release the spring and have it do positive work, pulling that way and going that way. So a potential energy is the energy a system has due to its position, shape, or configuration. There are lots of ways. So here's I can adjust the configuration on this thing, or you can call it the shape. By stretching the spring, I change its shape. There are lots of different ways to change the shape of things. I can take a marker and I can bend it a little bit. If I bend it a little bit, now it's kind of springy. I've stored some energy by changing its shape, or I can adjust the position of this in a gravitational field and raise its potential energy that way. Potential energy is stored energy that is completely recoverable, right? When I do work against gravity like this, I'm storing energy in the marker, and the energy is completely recoverable because I can just drop the marker and get all the energy back. Okay, so what kinds of forces produce potential energies? Clearly friction doesn't. If I drag this marker across the table here and friction works against it, I can't release it and have it go back the other way. That energy is lost. And so certain types of forces called conservative forces, which you can kind of tell by looking at them, springs, gravity, things like that, things that kind of bend a little bit. You can often, those are often forces for which the work done depends only on the position and not the initial and final positions, not the path taken. So if I take this spring and I do positive and negative work for a while, really at the end of the day, the energy that's stored in it just depends on where I started and where I ended. And that's also true of the work I do on it, because if I stretch it way past the position that I finish up at, and then I release it, now I'm doing negative work. So I'm doing positive work, and now I'm doing negative work and getting that energy back. And so all that matters in terms of how much energy is stored is where I started and where I finished. So those are so that's what a conservative force is. A conservative force is a force that for which the work done depends only on the initial points and final points, and not on the path taken, not on how we got there. Same thing with this. If I lift a marker in a gravitational field and raise it, I guess I can pretend I'm going up and go this way, right? If I raise the marker this way, it just matters where I started and where I finished in terms of how much potential energy it has and how much work I had to do to get it there. As long as there's no friction type forces acting, as long as there's no non-conservative forces, then it only depends on the endpoints and not on the path taken. So we can define a potential energy for any conservative force. We already did it for gravity. We said for gravity, the potential energy is mgh. The work done against a conservative force to reach a final position depends only on the initial and final position. So next we're going to do potential energy for a spring, right? We just did what formula for potential energy for gravity was, it's m times g times h. Another conservative force is the force due to a spring, and we already gave a formula for that. It was some constant times the change in length of the spring. But now we're going to write that as a potential energy. So we're going to talk in this section about the potential energy due to a spring. This uses Hooke's law, which we already talked about. Hooke's law is F equals kx. And so the force to stretch a spring a distance x from its equilibrium position, in other words, it starts at rest. It starts in its relaxed state, and now you pull it out some distance, you stretch that spring out, right? If you're going to stretch it a distance x from its equilibrium, the force to get it there is F equals kx. So the bigger x is, obviously the bigger the force is. X starts out at 0 if it's at equilibrium, and then each little bit you stretch it further requires you to increase F, right? Because F depends on how far it's stretched. So if I stretched it 1 centimeter, and then I stretched it to 2 centimeters, I would have to double my force. And if I want to go to 4 centimeters, I have to quadruple my force. If I want to go to 5 centimeters, I have to have 5 times the force for 1 centimeter, and so on. K in this equation is called the spring constant, and it's a measure of the stiffness of the spring. The bigger K is, the harder it is to stretch the spring. So if we want to calculate the potential energy, we first have to look at the work done stretching the spring, because that's how much potential energy gets stored. However much work I do stretching the spring, remember when we did potential energy due to gravity, we said, look, however much energy I spend lifting my marker up, raising the marker, right? That's how much energy gravity is going to give me back. And so the work I do to stretch the spring is the energy the spring stores. And so the work done is just, if you remember our formula, it's force times distance. Technically, there's a cosine theta in there, right? Work is force times distance times cosine theta. But with springs, we always assume that that's all in a line. That is to say, the spring is moving in the direction I'm pulling, and there's no angle between my pull force and the stretch, right? And so we drop the cosine theta out, we assume theta is 0 and cosine theta is 1, and we say the work is just the force times the distance. So we could use this to calculate the work done and the potential energy and so on. But the problem is the force is not constant. And so we don't know what value of the force to use. When I'm first starting to stretch the spring, it takes a very little force to stretch it at the beginning. But as I pull it out, it gets harder and harder to stretch it. And so what we do is we say, well, we're going to use the average value of the force in this formula. We're going to say the work done is the average value of the force times the distance. Well, the average value of the force is just the average between whatever its maximum value is, which is kx, and 0, because its value is 0 at the very beginning. There's no force acting on it here. And so I pull very gently and I get a little bit. The harder I pull, the more I get. And so the average over the course of that distance is just halfway between the 0 and the maximum value. And so the average force is 1/2 kx. The distance it's stretched is still just x. And so the formula for the work done is 1/2 kx squared, and that's the potential energy due to a spring. So here's a simple spring problem. Here's the idea. The spring has a constant of 1,000 newtons per meter, and it's compressed 10 centimeters. And so here it is in its relaxed position. This is a spring that's getting squished, so maybe that's not the best example. But it's relaxed like this, and I push it all the way in like this, and then I put a marble on it and release it, and it shoots the marble out, right? And so we want to look at this from the standpoint of first maybe work and then potential energy, and we want to calculate the kinetic energy. I'm going to kind of go through the whole work process, and then I'll show sort of a straightforward, simple way of solving this problem. But if we look at this from the standpoint of work, the whole compressing process, we can say, look, as I'm pushing this in, I'm doing positive work because I'm pushing this way and the spring is going that way. But the spring's doing negative work because it's pushing the other way, and but it's going this way. Never mind the marble yet. It's just me pressing the spring, loading in the spring. If you want to, I can erase the marble for the second, because we're just going to put the marble on at the end and shoot it, right? And so this is me loading the spring. And so this process, if you go to the work energy theorem, remember the one we wrote down at the very beginning, we said the work done is equal to the change in kinetic energy, right? Well, the work in this process is the work by me plus the work by the spring. And since I start out at rest and I end up at rest, the change in kinetic energy is just 0. And so the work by the spring is just minus whatever work that I do, right? Well, we've already decided the work by me, right? Because we've looked at springs before and we said, look, if this is just the work by me is just the average force I apply pushing this way times the distance. And we said since the force to compress a spring is kx, the average force going from this point to that point is just 1/2 kx, right? Times the distance I've compressed it, which I've said is x. And so that's 1/2 kx squared, or the work by me is, that's the work by me is 1/2 kx squared. And so the work done by the spring is minus the work by me, which is minus 1/2 k x squared. And what we said is whenever the spring is doing negative work, that's storing energy in the spring. You can see the spring's pushing this way, I'm pushing this way. When the spring goes backward, energy is getting stored. And so the potential energy stored in the spring is negative the work done by the spring. And so negative and negative is positive, and so the potential energy stored is 1/2 k x squared, right? And so if I wanted to, I could say, look, once I'm at this position, now let's say I put a little hook there so that it's just stationary in this position, right? And now I'm getting ready to release it. And so now I could say, look, I could operate this equation again. I could say the work done is equal to the change in kinetic energy. But now I'm talking not about compressing the spring. The spring's already been compressed. Now I'm talking about from here, I put the marble on here, right? And I'm going to say, look, this is going to be the work done by the spring is equal to the change in kinetic energy. Once the spring's out here, it's got no energy, right? It's in its relaxed position and it's not moving. It's all in the ball. And so the work done by the spring is equal to the change in kinetic energy of the ball, right? And so, but the work done by the spring is now positive. Positive 1/2 k x squared. And that's equal to KE ball final minus KE ball initial. The initial kinetic energy of the ball when it's here is 0. And so I can say, look, 1/2 k x squared is equal to 1/2 m v squared, where that's the v that I'm talking about, right? The halves cancel, and I get v is equal to, or v squared is equal to k over m x squared, or I'll come back down here, v is equal to the square root of k over m times x, right? And if I evaluate that, k over m is 1,000 newtons per meter over 0.025 kilograms square rooted times 0.1 meters. Right. Well, 1 over 0.25 is 1 over 0.025 is 40, so this is the square root of 40,000, which is 200 times 0.1, which is 20. You can check that math on your own. This is 20 meters per second. And so that's the speed. The work done is the change in kinetic energy. Okay, now I'm going to do the same problem just a little differently, the way I would say normally do it. We looked at all the work done in here, right? And so now I'm going to look at it from the standpoint of potential energy. And so I'll just erase the stuff we did. You can freeze on that and look at it if you want. And I'm going to say, look, the work done by the spring is minus the change in potential energy of the spring. That is to say, when the spring is doing negative work, the potential energy is increasing. When the spring is doing positive work, the potential energy is decreasing. That's what the minus sign is there for. And so I can say, look, the work done by the spring, since it's the only thing that's doing work, is equal to the change in kinetic energy. This is going to look just like the gravity problem we did. And so that means minus the change in potential energy of the spring is equal to the change in kinetic energy of the ball. Or I can say the change in kinetic energy of the ball plus the change in potential energy of the spring is equal to 0. Remember when we were doing the gravity problems, I would say, look, if there's no outside forces like friction or me or anything like that, if it's just gravity in the object, you just put the kinetic energy and the potential energy on the other side of the work equation. and you can just leave the work out because the system is closed and mechanical energy is conserved. And so I would have just started this problem with this equation. I would say, look, the spring is storing potential energy. It's 1/2 kx squared. The marble gets potential energy. The ball gets potential kinetic energy. It's 1/2 mv squared. And so I'd say Ke final minus Ke initial equals Pe final minus Pe initial. And so Ke final plus Pe final equals Ke initial plus Pe initial, right? And so the initial kinetic energy is 0, right, because my ball's at rest. The final potential energy is 0 because my spring is not moving anymore and it's not stretched. And so this gives me the exact same equation. 1/2 mv squared is equal to 1/2 kx squared, or I get v is equal to the square root of k over m times x, which is what we just got a minute ago, 20 meters per second. So again, I would probably be starting, I would recognize that this is a conservative force, so it's got a potential energy, and then if I don't have any other forces acting like friction, I can just say, oh, change in kinetic plus change in potential equals 0, and I don't have to worry about the work.